Hello and welcome once again for another advanced engineering math example problem. So this is day 1, example problem 2. And the question is to state the order of the ordinary differential equation and verify that the given function is a solution to it where c is a constant. So we have a differential equation, y prime is equal to 1 plus y squared, and the solution given, which is a family of solutions, is y is equal to tangent of x plus c, where c is some constant. Now, to verify a solution, basically what we have to do is substitute this in for y. Okay, so the left-hand side is just going to be y prime, so we have to take the derivative of this, and then verify that if we substitute y in over here, that we get the same exact thing on the left and the right. If that's the case, then this is a solution to the differential equation. Now, the first part also asked to state the order of this differential equation. Well, we can clearly see that the highest number of primes, if you will, is a single prime, which means it's a first order differential equation, right? dy dx. If it was d squared y dx squared, then it would be a second order differential equation, and so on. So the highest order here is the first derivative, and therefore it's a first order differential equation. Now the second part is, well, we have to, as I mentioned, we have to find y prime and make sure that that is actually of this solution. So take the derivative of this solution with respect to x, and verify then that if I substitute in y for y squared, that I get the same thing. So here's what we're going to do. We're going to note that tan of x is equal to sine of x divided by cosine of x. Now, you could immediately, by the way, stop here because and take the derivative, because we do have something known as the quotient rule for derivatives, as you should remember. However, I prefer to simply use the product rule, so I can rewrite this as sine of x times cosine to the minus 1 power of x, okay? And this way I will be able to use the product rule when I take the derivative. So when I take the derivative of that, well, I can use, again, the product rule, but notice that I have an x plus c in here, so I'm going to also have to use the chain rule. The derivative of sine of x plus c, well, when c is just a constant, it just shifts x by something, so I could sort of replace it with, I could think of x, my term inside of here, by the chain rule, actually. This, if you really want to work this out, you can use the chain rule to verify that this is true as well, but effectively what ends up happening because of the chain rule is that the sine of x plus c, the derivative, that's just cosine of x plus c. Okay, and it's a similar concept here. The derivative of cosine to the minus 1 power ends up being minus cosine of x plus c to the minus 2 power. That's the first part of the chain rule, times the derivative of what was on the outside, which is cosine was on the outside, so that gives me minus sine of x plus c for the second part of the chain rule there. And what we end up getting is the sine of x plus c divided by the cosine of x plus c squared. So now we can use the product rule, because we found the derivative of the first part and we found the derivative of the second part of this multiplication of functions here. And obviously from the product rule we can just take the multiply So we take the 1 over cosine, basically, cosine to the minus 1, times the derivative of the first part, which was cosine, so that obviously just becomes 1. And then the second part is, well, we take the derivative of the second part, which is written right here, sine over cosine squared, and multiply it times the first part, which is sine, and we get sine squared over cosine squared, well, of x plus c. Well, we know that tangent is sine over cosine, so sine squared over cosine squared must be tangent squared, which is exactly what we find. Thus, we find that y prime is equal to 1 plus tangent of x plus c all squared. Now, we have to verify that if I plug tan of x plus c in for y on the right-hand side, that I get the same thing. So I should get 1 plus tan squared, 1 plus tan of x plus c squared, if I substitute in tangent of x plus c on the right-hand side. Well, the right-hand side was 1 plus y squared, and we had y equal to tan of x plus c, so that means that 1 plus y squared is 1 plus tan of x plus c squared, which is exactly the same as what we found here for y prime. So my right-hand side and left-hand side are equal, therefore it is a solution. Tan y equal to tan of x plus c is a solution to y prime equal to 1 plus y squared. That's all that I have for this video. Hope to see you again soon.